First of all, let me introduce myself. I'm Jay Sharping, and I'm filling in. Unfortunately, I missed the class on Monday, so I want to make it up to you by creating a quick little video with the material. The material is mostly about Newton's second law, statics and dynamics, and let me just review a little bit of that with you. If I can advance the slide. Okay, so remember, Newton's first law says that things remain in motion unless acted upon by a force, and that means constant velocity. So velocity is a vector and it has magnitude and direction. So as long as its direction or magnitude does not change, the velocity that is, then that object is not being acted upon by a force. The second law states that the net force on an object, and it's important that you pay attention to the net force, which is the sum of all forces acting on that object is equal to the mass times the acceleration, where the net force and the acceleration are both vector quantities. We can make a great deal of progress with Newton's second law, and there's a very interesting case, which is when the net force is equal to zero. That means that there's no acceleration. So let's do a sample problem that has to do with the net force being equal to zero. So here it is. Let's set it up. Newton's second law and equilibrium. Equilibrium means that the state of motion of that object is not changing. So we have a steel beam that's being supported by a couple of ropes from above, and it's just staying still, right? We know that there's some tension in each of the ropes that is pulling upwards, and there's the weight of the beam, which is pulling downwards, and we can use Newton's second law, where the net force acting on that beam is equal to zero, and that's what we're going to go ahead and figure out next. Well, let's go ahead and set up this problem. What I want to do is to first of all figure out what the givens are. Okay, the things that we're given are that the mass of that object is equal to 1,000 kilograms. We were given that one of the angles, I'll call it theta 1, is equal to 20 degrees, and theta 2 is equal to 30 degrees. And that we have a static situation. The static situation means that the velocity is equal to zero and the acceleration is equal to zero. The important one really is that the acceleration is equal to zero, because that allows us to use Newton's second law in a particularly useful way. Let me redraw this so that we know what's going on here. So again, we have this girder, which is set up like this. Let me undo that here. It's suspended by two wires or ropes. Okay. Here's theta 1. Here's theta 2. Here's the girder, right? So one of the things that we need to do is to find the tension in each of the ropes. That's actually what is being asked for. So here's T2, here's T1. And the most useful diagram that we can make, besides this diagram here, which illustrates what's happening, is a free body diagram. So let me go ahead and do that. Okay, so the free body diagram is a simplified version of this. Okay, this object is going to have a weight, which I'm going to call just W. Right, that's pointing downwards, and it's equal to M times G. There are two tensions. One of them is going up like this, T2, and the other one is going up like that, T1. Well, this free body diagram allows us to make good use of Newton's second law. Okay, Newton's second law says that the net force on an object is equal to the mass times the acceleration. Let me write this over here. So the net force, so vector quantity, is equal to the mass times the acceleration. Okay. In this case, the acceleration, as I mentioned, is equal to 0. So this is going to be equal to 0. Simplifies things. I love it when stuff is equal to 0. Okay. The fact that this is a vector equation means that we get to solve it in both dimensions, in the x direction and the y direction. So let me go ahead and just first set up what's happening in the x direction. So let me just indicate this. So I always like the x direction going this way and the y direction going this way. It's just a habit I've gotten into over the years, and I've been doing this for a while, and old habits are hard to break, so that's the way we'll do it. And that means that the net F in the x direction is going to be equal to this component of T2 combined with this component of T1, right? Okay. I don't want to put those on the free body diagram, but let me redraw it so that we can see it. So T2 is like this, right? We have T2x, and eventually we will worry about T2y. And we also have a similar vector. We have T1, which has T1x in this direction, and T1y in this direction. Very good. So we need to figure out those components. Remember, the angles that were given were these ones, so we just have to be a little careful with that. Okay, but the net force in the x direction then is going to be equal to T2x minus T1x, okay, where I've taken account of the fact that the T1 is pointing in the T1x is in the negative direction. And if I do my SOHCAHTOA stuff really well, what T2x is going to be is T2 times, let's see, so this angle and this angle is the same, so it's going to be equal to T2 times sine of theta 2 minus T1 times the sine of theta 1. And this, of course, is still going to be equal to 0. This means that I can solve one of these and maybe use it in another equation. I'll wait for that. Okay, let's look at the y components. Okay, I'll just make a little separation here. So net f y is also going to be equal to 0 eventually. That is going to be equal to T1 y plus T2 y minus the magnitude of the weight. Again, I've taken account of the directions here, okay? So all the numbers are positive. I put the directions in the signs. All right, so T1y is going to be, let's see, I'm looking at T1y. It's going to be the cosine, T1 cosine theta 1, right? And plus T2 cosine theta 2, and then I have to subtract mg here. Well, we're getting somewhere. Now we have two independent equations. The x and y components of the motion are independent, and we have two unknowns, T2 and T1. Okay, so we have a system of equations that we can solve pretty easily. So for example, I can solve for T2 over here. Okay, it turns out to be equal to T1 sine of theta 1 divided by sine of theta 2. And then I can use this thing and plug it in over here and solve the y component equation for T1. Then I can get a number for T1 and plug it back into the x component equation. Let me go through a little bit of the nauseating math for you, since maybe I do it a little differently than Professor Strubba does. So I'm going to just go ahead and substitute T2 into this equation and solve for T1. So I'm going to wind up with T1 cosine theta 1, and then I'm substituting in T2, so I'll have a plus T1 sine theta 1 divided by sine theta 2, and then I need to multiply by cosine theta 2 minus mg, and this is all equal to 0. I can solve this for T1. So that's going to be equal to mg times a big sloppy looking thing, so 1 over. So I've moved mg over on one side of the equation. I've separated out T1, and then I'm taking the quantity that multiplies T1 and putting it in the denominator on the other side. So I'll have a cosine theta 1 plus sine theta 1 sine theta 2 times, well, that's supposed to look like a cosine. Cosine theta 2 okay, and if I plug in numbers, what I will get here is that T1 is equal to 6,396 newtons. Okay, none of these things, like none of the thetas, have any dimensions, right? The only dimensions are m times g, so that'll give me kilogram meters per second squared, which is newtons. And however, we were given all of our numbers to 3 significant figures, so this figure is not significant. So the proper way to write this would be 6,400 newtons, 6.4 kilonewtons. Okay, there we go. So that's one of ours. And then we can just take this number here, right, and plug it in up here to get T2. If I do that, I wind up with T2 being equal to 4,380 newtons. Again, I want 3 significant figures, and I want my dimensions to be newtons. If I'm going to assess whether or not these numbers seem reasonable, I can ask myself a couple of questions. One, did the dimensions work out? Okay, the dimensions were mass times acceleration, so the newtons is pretty good. The number here, it's like thousands of newtons. Sounds like a lot, but if we just figure out the weight of this object, it's going to be 1,000 kilograms times 9.8 meters per second squared. So that's, 9,800 newtons. Okay, so it's not surprising that these two tensions would be the same order of magnitude as that. Okay, and let's just make sure that we found what we were supposed to find in the equation, which was the tension of each rope.